Okay, so limits and their properties, part 2. We're going to look at, I guess, part 3 really, but evaluating limits analytically. And this unit in the book is really robust. We're going to take half of that and save it for the end of our unit. And the other half we're going to do right now because it's a little bit easier to get our hands on. So we're going to evaluate a limit using properties of limits, develop and use strategies for finding limits, and then evaluate a limit using a dividing out technique, simplifying a rational function. So properties of limits. First of all, the limit of f of x as x approaches c does not depend on the value of f at c. Okay, we had an example of that earlier when we were looking at an example where we had some function and then it did this, and then another function, another part of the function that maybe did something like that, and then somewhere in the middle we had this value, right? So if this is our function and here is c, the value at c is defined, but left and right of that, we're going off to our infinity in my terrible drawing. So in either case, we can evaluate the limit by direct substitution if we can evaluate this, right? So if the limit of as x approaches c of f of x is f of c, we can do that by direct substitution. Okay, direct substitution for functions that are continuous. This one isn't, right? You got to pick up your pencil to draw it. So if it's a continuous function, we can usually just plug it right back in. Such well-behaved functions, they clean the room, make their bed, do all the things that we would ask them to do, are continuous at c. So for example, the limit as x approaches c of b is a constant here. It says let it be a real number. Okay, so this would be like the limit as x approaches 4 for 12, right? Well, the function 12 just looks like this. It's 12 everywhere. And if I go out here to 4 and I look at it, I wonder what's happening at y. Well, we still know it's 12, right? That's equal to 12. So what about this one? This is the limit of as x approaches c of x. Well, if the function is just x, y equals x, that one's a little bit boring, but for any c value that we pick, because y equals x, we're going to get c back. Right, we plugged it in. And then here is some power of x, right? So maybe we have some cool function where it's like whoopie-doo. And if I plug in a value out here at c, because of this power function is an odd power of x, then we're going to just do whatever that c value is to whatever odd power we had. Okay, let's look at those. Limit as x approaches 2 for 3 is still 3. It's 3 everywhere. Limit as x approaches negative 4 for x is negative 4. And the limit as x approaches 2 for x squared is 2 squared, which is 4. Okay. So this one, you might want to pause the video, kids, and write down some of this because this is really kind of important for what we're doing. If we have some scalar multiple of f of x as x approaches c, we have the limit of f of x times that scalar multiple. This might look like, if we were taking the limit for this one, we took the limit as x approaches 2 for 2x squared. That's the same as 2 times the limit as x approaches 2 of x squared, right? It seems simple, but that's what it's doing. We could do direct substitution and then multiply by 2 at the end. Sum or difference, if we're going to have the limit of a function, like a polynomial here, we could do each individual part, find the limit of this part, find the limit of this part, and then add the limits together to figure out where it's going to go. And this is plus if it's plus and minus if it's minus. Product, quotient, and power. So we're going to go through examples of these, so it's not necessary for me to illustrate them every time. I just got excited about the first one, but here we go. So we're going to take the limit as x approaches 2 of the polynomial 4x squared plus 3. Well, what would that look like? Well, we can certainly break that up into 2 different parts because we have like f of x and g of x. And maybe we want to take the limit of each one individually. We also have that power rule here. So we could take out the 4 if we wanted to and direct substitute. So we're going to plug in 2 here. We get 4 times 4 is 16. And I can't really plug this in. We're just evaluating. That's still 3. And we get 19. This is reinforced by the graph. If we were looking at the graph, we would see what that looks like. It's just direct substitution anyway. I didn't have to break all this stuff up, kids. I could have just plugged in 2 into this part of the function and simplified. This understanding is great, but we're just going to do plug it in and see what happens, okay? The plug it in and see what happens method is fantastic, and it works for a lot of limits, especially all the polynomial limits. So plug it in and see what happens is our solution if we know it's a continuous polynomial. The limit as x approaches 2 of a polynomial function is simply the value p at x equals 2, which I just got done saying. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators. So it also works when we have some rational function where we're not dividing by 0. Okay, so limits of polynomial and rational functions, plug it in, or plug it in and make sure that we don't have 0. Essentially, this is going to be true for a lot of the limits that we're evaluating in calculus. That if I want to evaluate the limit of some function, and I decide, let's say this is some function w of x, and w of x might be, that doesn't look like a w, sorry kids, you're stuck with my handwriting. This limit of w of x, w of x could be a polynomial function. And I have some choices here, right? If I get just a constant, or w of c, then I'm good. If I get some value where it's some constant over 0, then we have bad news. Okay, this is when we can't evaluate it directly. We can't plug it in because we're going to divide by 0 in the universe. And if we get some other thing where we have 0 over 0, there's hope. Okay, so we get 0 over 0, that's not 1. But you're going to see that we could probably have divided, and that's going to be coming up here in a second. So if we look at this limit, and I try to plug in 1, I look at the denominator. Is that going to give me something bad? No. I can directly substitute, right? So if I plug this in, I'm just going to look at 1 squared plus 1 plus 2 over 1 plus 1. I get 4 over 2, which is 2, and I'm done. You might, no, that's it. That's all we're doing for that one. And there's a bunch of math that says it's actually what I just told you, okay? Here's a graph of this function, and we can see that this is defined there. Polynomial functions and rational functions are 2 of the 3 basic types of algebraic functions. The next theorem deals with the 3rd type, which involves a radical, okay? So if we have some root of x, we can take that same root of c as long as c is greater than 0. We can't take the square root or some even root of a negative number, right? So when it's saying when their index is even, we got to be careful that c is positive or just not negative, I guess. Okay. You've seen that the limits of many algebraic functions can be evaluated by direct substitution, and that is true. Direct substitution is where it's at. All the cool kids are going to at least try that first. 6 basic trig functions also exhibit this desirable ability as shown in the theorem below. In short, plug it in. Plug it in, see what happens. Sometimes bad things happen with tangent. So we got to be careful that it's in the domain, right? Because tangent has a limited domain, and so does all of these reciprocal functions, right? There's places where we have asymptotes, and if we have asymptotes, we can't plug those in. But any place else, we're good. So if we're going to take the limit as tangent x, or for tangent when x approaches 0, we're just going to plug in tangent of 0 and we get 0 back. That works. That's cool. X times cosine x. Maybe you don't know what that looks like, but we're going to evaluate it for pi. And we have pi times, what's the cosine of pi? Oh, that's -1. And we get -1 times pi, and we get back negative pi. What about the limit of sine squared x as x approaches 0? Remember, that's the sine of x quantity squared, and we know sine of 0 is 0, so we just get 0 back. Sweet. Okay, now we have a strategy for finding limits. We actually have lots of strategies. The most important one, if I haven't made this clear, plug it in, see what happens. That could be your saving grace. Sometimes the thing looks really gross, but if you would just try to substitute and evaluate the function, turns out there was never any problems with the limit there to begin with. If we have functions that agree at all but one point, then we can try to evaluate that. This is where we're like looking at this function. This is a difference of cubes, right? And we're looking at this and we cannot plug in 1. We can't plug in 1. But I can factor this, right? This is like x minus 1 times x squared plus x plus 1 all over x minus 1. And I notice, hark, there's something that's cool that's going to happen. And I can simplify this, and I get x squared plus x plus 1. Now, if we go back to our original thing, if I would have tried direct substitution, I would have had 1 cubed minus 1 over 1 minus 1. And I would have ended up with 0 over 0. And when we get 0 over 0, there's a good chance that something's going to simplify. And when I go back and I try to evaluate this simpler function, okay, this is a simpler function. This isn't the same because we don't have the restrictions when we're done simplifying it. But I'm going to do this simpler function that agrees, this function agrees with this function everywhere except where x equals 1. Because there's a hole in this one, right? So now I'm going to take the limit as x approaches 1 of x squared plus x plus 1 by direct substitution, because now nothing bad happens. So I get 1 squared plus 1 plus 1, and that's 3, which is probably going to happen when I animate the PowerPoint. Okay, so these are almost the same functions, except for that one point. That's what this whole little subsection is about. Factor, simplify, solve. So we're going to have to remember our factoring rules. And if that's not your cup of tea, you're going to have to really go back and review those or ask for help. So we have strategies for finding limits. This is still a strategy, 1, 2, 3. It seems like several strategies to me, kids. Even I can count past 1. All right. Learn to recognize limits that can be evaluated by direct substitution, right? If we can plug it in, we're going to plug it in. And really what you got to recognize is when direct substitution fails. If we plug it in and we get constant over 0, failed. If we plug it in and we get 0 over 0, fails for now, but could probably be simplified. And if we plug it in and we just get a constant, 75% or more of ours are going to be like this, right? I guess it depends on which problems I assign you. But then when you're out in the wild hunting limits, most of them are going to look like this. When the limit of f of x as x approaches c cannot be evaluated by direct substitution, we got to find a function that agrees for all but that point, right? Which is this. We're going to simplify. Or at the very end of the unit, we're going to learn how to rationalize. Or we can just use a graph or a table. Look at a picture. Try to figure it out. Now, you telling me on your test, hey, I just graphed it and looked at it, is not going to be okay if you're supposed to evaluate it analytically, which is what this whole unit, this subsection is about, right? So analytically, but if all heck breaks loose and you don't know what else to do, you can at least get some credit by using a graph or a table. That still works. To reinforce the dividing out technique, one procedure for analytic evaluation is dividing it out. Looking for common factors. Right now, if I tried to plug in -3, right, direct substitution, I have -3 squared minus 3 minus 6 over -3 plus 3. Well, here I have 9. Minus 3 minus 6 is 0 over 0, right? 0 over 0 means there's hope. Okay, there is hope. So we're going to go back and we're going to try to factor. When I do that, I'm making a simpler polynomial that agrees everywhere except at x equals -3. So I'm going to say, okay, well, what about the limit as x approaches -3 for, well, this is like x plus 3. They've had to match, right? So we kind of have a heads up on what might happen. And then x minus 2, and I double check it, and it works. And so this is going to be the limit for when these cancels. City, we get x minus 2. And now I can plug that in, and I get -5. So that's where it's approaching, even if when we try to plug it into the original function, we got a hole in the function. Okay. This is everything that they just talked about. We're going to post this PowerPoint so you can come back and look at it if you're interested. But look, I got -5 just like I did a minute ago, and without all the slides. In example 7, direct substitution produced a meaningless fraction of 0 over 0. That's the indeterminate form because you cannot determine the limit. Not like it is, but we can divide out common factors, which means there's hope. These last 3 are ones that you need to memorize. Please take a minute and look at those. Pause the video, write them down, make sure that you memorize these because we have to use the squeeze theorem, which we're going to learn at the end of the unit, to prove these, but it's just much faster to us if we just say, oh, I know that the limit of these 3 are 1, really, because sine divided by cosine or whatever is still 1, right? 1 times 1. There we go. So check those 3 out. Kids, there is analytical limits. To recap, plug it in, look what happens. As long as we don't have a constant over 0, there's still hope, and we're going to look to substitute, or not substitute, we're going to look to simplify. And if we get a constant over 0, probably the limit doesn't exist.